All right, today we're going to prove two theorems that I told you about last time about the weight of Boolean functions at degree 1. And if we get time, we'll also start talking about an introduction to hypercontractivity. OK, so here are the two theorems. I'll state them for you. The first one, the Level-1 theorem, says the following. Let f be a function. And for this, I prefer it to go into 0, 1 with expectation alpha. Think of that as less than a half. OK, and think of f as the indicator of some subset of the Boolean cube that's small, of volume alpha. Then f has an unusually small amount of Fourier weight at degree 1. OK, so at most alpha squared log 1 over alpha. OK, since the total Fourier weight is the expected value of f squared, which is alpha, this is quite small compared to what it could be by Parseval. Actually, when we get around to proving this, we'll actually prove it in slightly more general setting, so I may as well state that now. We can even prove it for functions whose range is the interval -1, 1, if we replace alpha by expected value of absolute value of f. OK, so but if you want to forget about that, just think about f going into 0, 1, and it's the same statement. We just happen to be able to prove this slightly stronger theorem when we get around to it. OK, that was one. And then the 2 over pi theorem says the following. Let f be a Boolean function into -1, 1. And assume that all of its degree 1 Fourier coefficients are small. For all I. Then its weight at level 1 is not much bigger than 2 over pi. And actually, if it's close to that, so it's at least 2 over pi minus epsilon, then f has to be close to an LTF. A linear threshold function, in fact, to the sign of its degree 1 part. This purple is not so great. So as I talked about last time, the weight at degree 1 is some kind of proxy for the noise stability of the function for small values of rho. So these are both kind of like isoparametric theorems. This one says that small sets, indicators of small sets cannot have very high noise stability. And this one says that among sets, let's say, of volume a half, we know that dictators and antidictators are the most noise stable. But if you kind of rule them out by assuming that no coordinate is influential, or even this weaker assumption about the degree 1 Fourier coefficients, then the weight at level 1 is at most 2 over pi. And that's achieved by linear threshold functions. And in fact, it kind of robustly characterizes them. Yeah?
Should I be reading anything into the different colors on the first theorem?
No, the red is what the initial statement I told you last time was. But the purple is some like generalization that you can happen to make, as we'll see when we do the proof. It doesn't seem like that answered your question.
Well, we don't. So we don't. We don't know that. Do we know a lot about functions that go into 0, 1? Don't we usually? Because usually it goes into -1, 1, and that's where we have all the nice theorems about expected value is the first one. But when it's 0, 1, we don't.
Most of, I mean, we have a lot of theorems just about functions that map into the real numbers even. I mean, all these things like Parseval and so forth hold for those. I don't know, usually we make the convention that the range is ±1, but We could have done that here. It's just then you would have to make alpha equal to something like the variance of f. We're just trying to talk about the situation where you have the indicator of a small subset of the cube. And then it's sometimes more natural to use 0 and 1 because then the expectation is equal to the fractional size of the set being indicated. OK, so I'm actually going to, both of these theorems kind of, the proof follows a similar strategy. So I'm actually going to take some time to explain the strategy before actually just diving into the proof. So let me talk about the proof idea. OK, and so for here, let me go back to the original statement. And let's assume f is a function into 0, 1. Again, think of it as the indicator of a subset of the cube. And let me write alpha for its expectation. OK, you can still be thinking of this scenario as well. In this case, think of perhaps alpha as being a half. OK. Now, we're interested in the weight at level 1. So let's actually let L, capital L, be the real valued function, which is actually what I've called f equals 1 here, just the linear part of f. OK. OK, so one thing I want to say is that the weight at level 1 of f is equal to the expected value of f of x times L of x. Can somebody tell me why that's true?
Sorry, just a question here. L here is the same thing as this f equals 1 doctrine, right?
Yeah, that's right. OK, can somebody? Yeah, that's right. Plancher L. It's just the sum of the products of the Fourier coefficients of these guys. And evidently, these are the Fourier coefficients of L. So they're just non-zero for degree 1 terms. And they're the same as f. So you exactly get sum of f hat I squared. OK, so think about it this way. In fact, think more about this theorem for a second, where alpha is small. So you choose x uniformly at random. L of x is given by this. It's like a random linear form. So it's a real number. It could be large. It could be small. We're trying to, by the way, upper bound this. So this sort of random variable, L of x, can be large or it can be small. But f of x is either 0 or 1. OK? Furthermore, it's 1 exactly alpha fraction of the time. So how could you upper bound this? Sort of the worst case, if like f and x could be decoupled even, would be if f was 1 exactly on the alpha fraction of x's for which this value is largest. Right? If you get to like pick an alpha fraction of the probability space so as to maximize this, you'd take it, if you could, to be all the points where L of x is largest. OK, so this is just a proof idea. So the things I might write down here might not be 100% accurate. But what I want to say is that this is at most expected value of the indicator that L of x is at least t times L of x, where t is chosen such that this event occurs with probability alpha. OK, actually, that's essentially 100% accurate. I suppose like if L of x takes some values multiple times, you might not be able to get this exactly alpha. But just assume that L of x has distinct values. At least I hope the idea is clear. I mean, if you just pick some t such that the probability of L exceeding t is exactly alpha, then this is the worst. This is the worst that this could be if f is always 1 on these big values and 0 elsewhere. Does that make sense? Okay, so a good thing is this kind of thing is analyzable using like Chernoff bounds in some cases, or in this case, it's analyzable using the central limit theorem, because L of x is just like a sum of independent random variables. Okay, so let's think about that a little bit more carefully. So now we've kind of all boiled it, and now there's no more f, and we've kind of just got it down to analyzing this random variable L of x. Okay, so can somebody tell me the mean of L of x? Feel free to shout it out.
0.
0, good. Okay. Can somebody tell me the variance of L of x? Since its mean is 0, that's also known as the expected square. Yeah, it's the sum of the, we know, it's like the sum of the squares of its Fourier coefficients, non-empty ones, which is just this. So it's actually exactly equal to the weight at level 1 of f. Okay, so that's good, because that's actually the thing that we're trying to bound in both of these theorems. Okay, so we're still in the proof idea zone, so let's just suppose that all of these f hat i's are small. Whatever that means. That's the hypothesis we have in this one, if not necessarily that one. Then we're exactly in the position of the central limit theorem, or more specifically the version with error bounds, Berry-SAN theorem. Right? We have just like a sum of random variables over the form constant times plus or minus 1, a random bit. And we're assuming all of these coefficients are kind of small. So what that means is then we expect L of x should be somehow distributed like some Gaussian. Let's call it z. And which Gaussian? Well, the one with the same mean and variance as L. Okay, and we know the mean and variance of L is 0 and sigma squared. So let me call this sigma squared. Okay, so then if we believe this, now we can analyze. There's like a computation. I mean, if we just pretend that this L of x is a Gaussian z. Okay, so for example, for the 2 over pi theorem, or imagine, imagine alpha is a half. Okay, so you're talking about functions indicating sets of volume about a half. There's actually no such restriction here, but these are probably the ones that are going to maximize the weight at level 1. How can we analyze this quantity? Especially if we imagine that this thing is approximately the expected value that z is greater than or equal to t times z. By the way, any questions so far? Okay, so yeah.
Why is that exact? How do we know there's anything specific?
Yeah, this is a slightly shady statement, but if you imagine that, imagine like a histogram of L of x's values. Maybe L of x. Maybe these are like the values which L of x can take on, and these are the probabilities with which it takes on that value. Then we're just looking to find the t such that the probability mass here is like alpha. Okay, and it's slightly shady because maybe like there's not exactly one t such that this is exactly alpha because, well, it's not like this is a continuous probability distribution, but we're still doing the proof idea, so we can ignore that a little bit. That said, in this picture, imagine we're thinking about the 2 over pi theorem, and alpha is a half. What does that mean t would be? Yeah, 0. We want t is supposed to be such that this is true. Okay, so if alpha is a half, you're looking for the t such that the probability that L exceeds t is about a half. Well, L is like a symmetric random variable, and especially if you're pretending it's a Gaussian, that's also symmetric about the origin. Okay, so it's the probability that it's non-negative is a half. Okay, so then it's like we want t equals 0. Okay, so then continuing in this case, then using this crucial theorem or fact, sigma squared, which is what we're calling the weight at level 1 of f, is at most approximately, using the central limit theorem, again, we're being a little flexible with the truth here, the expected value of the indicator that z is at least 0 times z. Okay, so really, if now we imagine plotting the PDF of z, the PDF looks, well, it's a Gaussian, it looks like this. And we're basically integrating z times the indicator that it's non-negative. Okay, so this is actually just a calculation which we can do. By symmetry, this thing, let me just put a star or something. By symmetry, star is equal to half the expected value of the absolute value of z. Right? So remember, that's, to use some bad notation, the expected absolute value of normal with mean 0 and variance sigma squared. Okay, and that's like sigma times the standard normal. So that's sigma times the expected absolute value of a standard normal. And we did some calculation a little while ago. This is just some number. It happens to be root 2 over pi. So that equals half sigma root 2 over pi. Okay, so sigma 1 over root 2 pi. So finally, we have sigma squared less than or equal to sigma 1 over root 2 pi. So if we divide by sigma and square, we get sigma squared is at most 1 over 2 pi. Okay. Well, there was like an approximately here because we used the central limit theorem over here. So we got the weight at level 1 is at most 1 over 2 pi. We were supposed to get 2 over pi, so what happened?
Was it not on purpose?
Everything is right so far, but it's up to you to resolve this issue at the end. Or before we get to that, is there any question about what we've done here? Get over. Okay, I encourage you to look at the top line of the middle two board panes. So the top lines of that.
The 0, 1, and -1.
Yes, thank you, Arda. Yeah. In this theorem, you're talking about functions to -1, 1. But here, it's like, oh, let's have them go into 0, 1. So that is the issue. You see, if f's range here is -1, 1, and we want to apply all these calculations we just did, they were about functions mapping into 0, 1. So we would say, I don't know, let f prime be a half minus a half times f. That guy has range 0, 1. And so we just deduced by all these calculations that the weight at level 1 of f prime should be at most roughly 1 over 2 pi. Okay, but we just this is f prime, which we got by doing something with the constant term and like multiplying by a half. Okay, which has the effect of multiplying the weight at level 1 by a quarter, because that involves squaring. So this is the weight at level 1 of f times a quarter. Okay, so now if we put the 4 over here, we get 2 over pi. Okay, so that was not quite a proof of anything, but that essentially will be the proof of the upper bound. We didn't talk about this part yet, but we will eventually. Well, you look a little bit stunned, so we'll do it all again for a proof idea of this level 1 inequality. So in that case, we're not imagining really that alpha is a half, but we're imagining that alpha is some small number. Okay, so I still want to do this and let L be the degree 1 part and make this observation that the weight at level 1 is at most this. The expected value of the indicator that L goes above this threshold t defined this way times L of x, excuse me. And you note that L of x is this sort of degree 1 random linear form with mean 0 and variance equal to the weight at level 1, which we also call sigma squared. Okay. Well, first thing we need to sort of understand is now in this new frame of mind where we think of alpha as being small, what is this t? T is supposed to be defined by this relationship. And we're kind of pretending if this is the sort of probability mass function of L, we're sort of replacing it by the PDF of a Gaussian Z. So for alpha small, T is sort of defined by the probability that, let's say, Z is at least T is alpha. Again, this is essentially a kind of explicit relationship because Z is a Gaussian. Okay, so this is like the probability that, as we saw before, sigma times a standard Gaussian is at least T, or the probability that a standard Gaussian is at least T over sigma. Okay, so you know if you have a standard Gaussian and like you're looking for the probability that it exceeds some large number, that's kind of like e to the minus that thing squared over 2. Okay, so since we're still working roughly, this is something like e to the minus this thing squared over 2. Okay, which means we can actually invert and get alpha. So if I were to sort of invert this equation, let me first take the ln and the reciprocal and get t squared over 2 sigma squared is roughly ln 1 over alpha. So that means t is roughly root 2 sigma ln 1 over alpha. Wait, that's a bit wrong. Okay, so if you pretend that L of x is like acting like a Gaussian with standard deviation sigma, then T is roughly, this is roughly the number such that the probability it exceeds this number is about alpha. Okay, really, you should go like root 2 ln 1 over alpha standard deviations. Any questions? Okay, no? All right. Okay, so we're just really trying to kind of complete this calculation. So here's our upper bound on the weight at level 1. It's this expectation, well, especially when we pretend we have z instead of the actual thing L. And now, let me continue it over here. Okay, so we saw that writing what's on the third board there, sigma squared, which is our definition of the weight at level 1, is at most, or approximately, the expected value of the indicator that z is at least t times z, where z is this Gaussian, and we know that this is t. Now, when you look at a Gaussian, it's very unlikely that it exceeds some large value t. And furthermore, like conditioned on it exceeding that large value, it's likely to be very close to t. I mean, this is going off like exponentially small. So like in the rare event that you're bigger than t, you're probably really close to t. All of which is a bit of a hand wave to say that, OK, first in this expectation, first you have to actually be bigger than t. Sort of, the probability of c bigger than t is exactly set up to be alpha. But then, condition on that, z, we feel, will be actually very close to t. Okay, so you'll kind of be getting a contribution from this part of about t, or maybe something a little bit bigger than t. Right, O of t if you want to get stressed about it, but it's actually pretty close to t. So what I'm saying is that this is basically at most alpha t, and here we have t, so that's like sigma alpha root 2 ln 1 over alpha. Okay, so again, we have this inequality with a sigma squared here and a sigma here. So we can divide by sigma and square. And we get sigma squared, which is the weight at level 1, is at most approximately alpha times 2 times ln 1 over alpha squared. Okay, and that was the bound for the weight at level 1 we wanted for such functions, even with the constant 2. Any question about that? Yeah.
So in the statement of the theorem, you said alpha less than or equal to 1.5, which doesn't seem to me to be exactly the same thing as alpha small.
Yeah, in the statement of the theorem, I wrote alpha at most a half, just because for alpha bigger than a half, you can look at 1 minus f. And because I didn't want to like get stressed about this being like a negative number. Really, the final theorem we'll prove is something like, OK, actually, you can prove literally this. I think for all alpha less than or equal to a half, we'll prove like 2 plus little o of 1 with respect to alpha. Alpha squared ln 1 over alpha. So actually, we don't want to. I don't actually want to make this precise. We're going to do the actual. When it comes to doing a formal proof, we'll do it like in a slightly different way. But this is the idea. OK. Also, I want to make one more comment here. In this proof, the main thing we really used was we didn't really use the central limit theorem like we did in the 2 over pi version. In the 2 over pi version, we really wanted it to be close to this Gaussian because we eventually looked at the expected absolute value of a Gaussian and like needed that was the special number root 2 over pi. here we didn't use quite so much. We basically kind of used like Chernoff bound or Hufting bound. I mean, it basically only relied on the fact that the probability that the random variable was some very large number was exponentially small in the square of that number. Okay, and that holds for anything that looks like this by Chernoff. You don't need to assume that these numbers are small, the f hat i's. Okay, so that's why we do not need that assumption in the level 1 inequality. Okay. So now I guess I'm going to, although I've shown the idea, I guess I'm going to prove it properly. So let's do that. Okay, so let me start over here. All right, so one thing that you decide to do once you try to prove it properly is note that it's like a little bit annoying that you carry all these like sigmas around. It's always better in life if you can like normalize your random variables so that they have variance 1, so that the central limit theorem gives you a standard normal. So one thing we're going to do for both proofs, and now I guess I'll start writing actual proofs for both theorems. We'll fork at some point. So let's say we're given f, which maps into the interval -1, 1. And let it be non-zero. Otherwise, everything is trivial. We're going to let sigma actually denote the same thing here, square root of the weight at level 1 of f. Okay, so sigma squared is the weight at level 1. But instead of this capital L, we're going to look at little l, which is just capital L divided by sigma, so that its variance becomes 1. Okay, so L of x is 1 over sigma times capital L. And we just do this so that the expected value of L of x is 0, as always. And the expected value of L squared, which is the variance of L, is 1. Okay, because the sum of the squares of the f hat i's, which is the weight at level 1, divided by sigma squared. Okay, and let me just write down this equation again. It's a fact, if you will. The expected value of f of x, L of x, which we sometimes like to write as inner product of f and L. Well, actually, it's a slightly different fact, I guess. This is 1 over sigma times the inner product of f and f, the degree 1 part of f, which is 1 over sigma times the weight at level 1 of f, which is sigma. Okay, so both these theorems, we want to upper bound the weight at level 1, which is sigma squared. So we're going to just upper bound sigma, which is this. Okay, so far I've just sort of started the bookkeeping. Any questions so far? Okay. So the first one we're going to prove is, I guess, the level 1 inequality. So to do level 1 inequality, we need to do this Hufting bound a little bit more carefully. Actually, this exact thing I just am erasing. Okay, but the fact is that we can do it without any central limit theorem or anything. We just need to go straight to the random variable we actually have. So this is a lemma. You can even actually forget about the setup and just think about it as a lemma that follows easily from Chernoff bound. So let L of x be, even you can think of it as a linear form over plus or minus 1 random variables, normalized such that sum of ai squared equals 1. And then for all s greater than or equal to 1, we have the following. Expected value over x, the indicator that absolute value of L of x is bigger than s, times absolute value of L of x is something like e to the minus s squared over 2. Okay? You need to put some small factor out here. Actually, it's kind of like we're doing this estimation and this board all in one shot. We're eventually just going to pick s cleverly to be like that t. Okay, we basically can do this calculation with Chernoff bound. You need to do a little clever trick at the beginning so that, Chernoff bound is about the probability of an event of a random variable being large, and you have something like the expected absolute value here. So let me just write down the trick instead of belaboring it. Let y be the following random variable. Expected value of L of x minus s. And the trick is, if you have like a non-negative random variable, y, then its expectation, it's at most, or it's equal to the integral from 0 to infinity of the probability that it's at least something, t, dt. That's for non-negative random variables. If it's not non-negative, then you should just put the indicator that it's non-negative here. Okay. Probably you've all seen that trick before, at least in the case that y is a non-negative random variable. It's not. It's a probability exercise. Okay. So let's rearrange a little bit. Okay, so given our values here, let's call this star. Okay, the left-hand side of star is equal to, well, you have the expected value of L of x minus s times the indicator that L of x exceeds s. And now I can expand this out and get the expected value of L of x times the indicator that L of x is greater than s. That's the thing we care about. Minus s times the probability that L of x exceeds s. Right, the expectation of an indicator. And now I'm happy because I can use Chernoff to bound this, or Hufting, or whatever it's called. Hufting, I guess. Since L is of this form and has standard deviation 1, this thing, if you just plug it directly into Hufting's bound, is at most e to the minus s squared over 2. Okay, so given that that's on the left-hand side of the, 2 times that, sorry. 2 because I have this absolute value. This is like the probability that L exceeds s, and this is the probability that L is less than minus s added together. Okay, so that, if you can go back to the lemma, that's where this like plus 2 times e to the minus s squared over 2 is going to come in. Okay, so it remains to bound the right-hand side here by this 2s e to the minus s squared over 2. Which I'll do. Any questions so far? Okay, so on the right-hand side, what do we got going on? This. Okay, so that's integral from 0 to infinity, the probability that L of x in absolute value is at least s plus t. dt. Okay, now I'll do a change of variables. U equals s plus t. So this is integral when t is 0, u is s. So s goes to u goes from s to infinity. Probability that L of x is at least u. dt is just du. Okay. Now from Chernoff bound or Hufting bound, I can upper bound this thing. Integral s to infinity of 2, just exactly the same as I did here. E to the minus u squared over 2 du. Now I have an integral that cannot be done in closed form, but here's a nice trick. I'll just multiply the integrand by something bigger. I'll multiply it by u. And that's valid since u is always at least s, and by hypothesis s is at least 1. And now, voila, I can integrate that, and it just gives, well, the thing that we want. In fact, I don't even need to erase this board. The antiderivative of this is e to the minus u squared over 2, so this is equal to there's some s missing here. Oh, this s is up here. Okay. This is 2 e to the minus s squared over 2. And this contribution is 2s e to the minus s squared over 2. Okay, I'm too lazy to write it all out, but if we rearrange everything, we get exactly this. 2e to the minus s squared over 2 from this part, and 2s e to the minus s squared over 2 from this part. Any questions about that? Okay, that was just an exercise in messing around with Chernoff bound to get something that intuitively seemed true to be true. Okay, so with that that lemma out of the way, we're now ready to finally actually prove these two theorems we set out to prove. So let's do it. Okay, so if you remember in our extended version of the level 1 inequality, which I said we could get for fun, we have f mapping into minus 1, 1, just like in this case. And alpha was defined to be the expected absolute value of f. Okay, but you can just think of f0, 1 value if you want. Okay, and let little l be as on this board. And we're trying to upper bound the weight at level 1. So equivalently, we can upper bound its square root, sigma. Okay, so sigma is the expected value of f of x, L of x. And now I'm just going to pick a parameter s to be named later and break this up according to whether L in absolute value goes bigger than that or smaller than that. So this is exactly equal to the expected value of f of x, L of x times indicator that L of x exceeds s plus the expected value of f of x, L of x, the indicator of the opposite event, L of x is at most s. Okay? Let's start with the latter one. Well, it doesn't matter. Let's start with the former one, let's say. For the former one, this piece, we're just going to use the fact that since f is at most 1 in absolute value, this is at most the expected absolute value of L of x times this indicator Okay, which by the lemma is at most 2s plus 2 e to the minus s squared over 2. Okay, I haven't chosen s yet, actually, but I'll choose it in a second. As for this guy, I'll do something also trivial. I'll just say, look, every time we have this event, the absolute value of L is at most s. So that means this piece is at most expected value of absolute value of f of x times s. Okay, and that's s times alpha by definition. Okay, so therefore, rewriting this, sigma is at most this thing plus this thing. And we just choose s to balance those two things. Okay, so roughly you have like s is going to be a lot smaller than 1 over alpha. You have alpha here. This thing is going to 0 real quick. So you just want to choose s a little bit big enough such that this thing is much smaller than alpha, so that this term dies. Okay, so that means you need to take s something like root 2 ln 1 over alpha. Okay, so choose s to make the first term negligible. Namely, we continue on this board here, now that we've used the lemma. Let's say, namely, s to be something like 2 plus times root ln 1 over alpha. Okay, maybe I'll write this. Okay, so then when you square that, divide it by 2, negate it, exponentiate it, you get something like little o of alpha. So then we get sigma is at most s times alpha times alpha. Okay. So if we square this, this 2 should be on the inside. If we square this, we get the theorem. Okay, and if you don't want to mess around with getting these 2's right, just call it big O of that. Take s to be a big constant times root ln 1 over alpha. Any question? Okay, so I feel that this proof has this proof I presented is the one due to a telegram from some early time. I can't quite remember. Just like in February, there's a new proof presented by Impagliazzo, Moore, and Russell, which is this long. It's very short, using entropy method. It's quite nice. This proof, although I took an infinitely long time to explain it, it's also pretty short, but probably the other one is even shorter. But this one uses just Chernoff bound, so I think it's relatively elementary. Okay, so that's level 1 inequality done. Let's do the 2 over pi theorem now. Okay, so for this guy, range of the function is minus 1, 1. And we also have this extra hypothesis that all of the degree 1 Fourier coefficients are small. OK, let me for now just work on proving the upper bound that the weight at level 1 is at most 2 over pi plus O of epsilon. OK, we'll let little l be just as on this board pane again. And we're going to assume that sigma, which is this root weight at level 1 of f, is at least a half. OK, why can we assume this? That's right. If it's less than that, otherwise, sigma squared, which is the weight at level 1, would be at most a quarter. And we're trying to show that it's at most 2 over pi plus epsilon. 2 over pi is point something, 6. Anyway, it's a lot bigger than a quarter. OK, otherwise we're done. And really, I only do this because we have this assumption that all the degree 1 Fourier coefficients are small. But when we make L, which is what we're going to work with now, we divide them all by sigma. So I don't want to divide them by a tiny number because then they get huge. OK, but since sigma is not a tiny number, we now have the analogous assumption that L hat I is at most 2 epsilon for all I. OK, great. So as always, we're trying to upper bound sigma squared. So I'll upper bound sigma, which is the inner product of f with L. OK, and here we'll just do something very simple and say that f is either plus or minus 1. So this is at most the expected value of absolute value of L of x. Actually, for this part of the theorem, not the converse part, but for this part, L could have even gone into the range minus 1, 1. OK. Now we're exactly in the position of the central limit theorem, or the Berry-Essayan theorem that we talked about before. L is the sum of ID things like AI, xi. Its mean 0, its variance 1, so it's close to a standard Gaussian. How close? Like O of epsilon close, since all the coefficients are at most 2 epsilon. So as we talked about last time, this implies that this is at most the expected absolute value of a standard Gaussian plus C epsilon. For some, this can even be like, well, it's a constant. It's a small constant. OK, and as I've told you several times, this number happens to be root 2 over pi. OK, and now if we just square this inequality, we get the first part of the theorem, that the weight at level 1 is at most 2 over pi plus epsilon. Any questions? OK, so now let's do the more interesting part. Well, not the more interesting part, but another additionally interesting part of this theorem, which is if that furthermore this is close to being tight, then f has to be close to being a linear threshold function. OK, so moving on to the next part. Suppose also that this weight at level 1 is at least 2 over pi minus epsilon. OK, so in other words, sigma is at least root 2 over pi minus epsilon, which is at least root 2 over pi minus, I don't know, 2 epsilon. So what that means is that, well, on the left-hand side here, under this assumption, we have this is at least 2 over pi minus something like epsilon. So actually, both of these inequalities have to be sharp to within constant times epsilon. In particular, this one has to be sharp, which means that it's sharp to within something like c plus 2 times epsilon. Okay, and let me just write this as the expected value of, absolute value of L of x is the same as sine of L of x times L of x. Okay, so let's take a look at what's going on here. X is a random, when x is chosen at random, L of x is some random variable. It's positive or negative, what have you. However, the expectation of this thing, okay, this is also always has the same sign as this. Right? If L is positive, this is plus 1 minus something that's either plus or minus 1. And if L is negative, this is minus 1 minus something that's either plus or minus 1. So really, if this is almost always, I mean, if this is really small, it's almost like this has to almost always be 0. Okay, it has to be that f of x is almost always sine L of x, which is exactly the conclusion that we're looking for, that f of x is almost always the sine of its linear part. Does that make sense? There's one catch there, which is like a little annoying, and I'll do it since we have time, which is that the other way actually this could be small is if like L of x was very small. Like on all those points x where L of x is small, you can't really conclude that f of x needs to be sine L of x, because they contribute like a negligible amount to this thing. So the only extra thing you have to do is argue that L of x is rarely super small. And you can do that using the central limit theorem, or Berry-SAN theorem. Okay, so let's just argue that. So I just want to say that L of x is not super small very often. So let's look at the probability that it's smaller than some, this is thought out well in advance, some constant k times root epsilon. So this is the probability that this random variable is inside the interval plus or minus k root epsilon. So we know by the Berry-SAN theorem, or central limit theorem with error bounds, it should be about the same as what it is for a the Gaussian, standard Gaussian. Okay, so that's approximately the probability that a standard Gaussian is in absolute value at most k root epsilon. Okay, so if you have a standard Gaussian, what's the probability that it's between plus or minus k root epsilon? It's this integral. It's at most the width of the interval times this height here, which is 1 over root 2 pi. So this thing is at most actually 2 times, well, 1 over root 2 pi times 2 times k root epsilon. And if you actually squint at the error bounds you get in Berry-SAN, they're on the order of epsilon, which is much smaller than this. So if you plug in what's actually known, you can just say that this thing is at most 2k root epsilon, if you're careful. Okay, this 2 is noticeably smaller than this 2 over root 2 pi. Okay, so now I'll just combine this fact and this fact to get the desired conclusion. Okay, and the desired conclusion is that f is close to sine of L of x. So let's look at the probability that f differs from sine L of x. In fact, let's suppose, for the sake of contradiction, that this is bigger than 3k root epsilon. Okay, we're going to get a contradiction, and then we'll say, therefore, f is this close to the LTF sign of L. Okay. Well, then we know that the probability that f of x differs from sign of L of x, and this unusual event happens. By a union bound, we'll just take all the probability mass here, subtract the upper bound and the probability of this unusual event, and we'll still have 1 times k root epsilon left. Okay, but whenever both of these things happen, f is the opposite sign to L of x, and L of x is big in absolute value, you get some sort of noticeable contribution here. So if we call this double star, you get that it's at least, well, k root epsilon at a time, this weird pair of events happens. And whenever it does, this number is 2 times the sign of L of x. So when we multiply it by absolute value of L of x, we get 2 k root epsilon, which is 2k squared epsilon. Okay, but it's supposed to be at most this c plus 2 epsilon. So this is a contradiction if 2k squared is bigger than c over plus 2. Okay, so just make whatever constant c was that came out of this error in the use of Bayesian theorem, just make k much bigger, and you get a contradiction. Okay, that's the end. That's the end of both proofs. Any questions? No? Okay, so now it's very calculation intensive. So we'll end the class by just chatting a little bit. I'll tell you what's coming up. So the next thing I want to get to is actually one of the most important topics in the area. It's this topic of hypercontractivity, which is somehow, it's like somehow considered the only non-elementary theorem in the area. And so any proof that uses it is considered like a fancy proof, and any proof that doesn't use it is considered like a simple proof. That's not always an accurate statement. But what I really want to tell you is that it's not even a fancy theorem. It's very simple. It hardly deserves the status of like a difficult or mysterious theorem. So actually, we're going to prove like a baby version of it, which is super easy. And then we're actually going to do almost all the consequences. Well, I want to convince you that almost all of the consequences that use this difficult hypercontractivity theorem only use this baby version, which is easy to prove. So everything should be considered easy. OK, so to explain this hypercontractivity theorem, I want to talk to you about random variables. And if you've ever done probability before, you'll know that random variables are sometimes very annoying, right? So they might never be close to their expectation, or they might almost always exceed their expectation, or they might almost never exceed their expectation. Or they could have first, second, and third moments small, and the fourth moment in infinity. Okay, all these very unreasonable, ridiculous things can happen, and it's very annoying. The computer science department has this thing called reasonable person principle. I don't know if the math people have heard of this, but it says that everybody is supposed to be reasonable, and we can all get along. So we want the same to hold for our random variables, so that nothing bad will ever happen. So it would be good if all our random variables that we ever dealt with were reasonable. And the exact definition of what that means is up to you. But actually, a very good way to quantify it, or a useful grasp on the notion, is to have fourth moment not too much bigger than your second moment. That sounds a little funny, but we'll see that indeed this makes random variables nice if they have this property. So let me turn that into a definition. This is a non-standard definition, as you might guess. So for b a real number, we'll say the random variable x is b reasonable if, as I said, its fourth moment, expected value of x to the fourth, is not too much bigger, at most b, bigger than its second moment squared. Okay, this also looks a little funny, but it's written this way so that the notion is scale invariant. Let me just say, if I take the fourth root of both sides, then I get, I hope you enjoy this notation, this is like the fourth root of the fourth moment. And then I get the second root of the second moment. Okay, this notation just means fourth root of fourth moment, and so forth, similarly. Okay, and as I said, it's written like with the expected second moment and then squared again, so that this is translation invariant. You see, if you take this random variable, sorry, scale invariant. If you take this random variable and multiply it by 5, both the left-hand side and the right-hand side go up by 5 to the fourth. Or in this version, both of them go up by a factor of 5, and they cancel. Okay, so this is done. This is scale invariant. Okay, so Cx is b reasonable if and only if x is. Okay, and I'll say in 1 second why this is a relatively good notion of being reasonable, although eventually we're going to explore some alternate related ones. Let me say that, on the other hand, this is, it's got a bad property. This is kind of a nice definition, but it has a bad property, which is that it's not translation invariant. Okay, if I take a random variable x and I add a scalar c to it, then this kind of goes haywire, and you can have the property that x is reasonable, but c plus x is not, and vice versa. That's a little annoying. It's kind of bad form a little bit in probability to define notions that change drastically if you like add a constant to your random variable. And actually, to eventually just fix that translation issue, we'll define an analogous thing called x is hypercontractive. And that'll fix the translation invariant thing. But this is still a perfectly good definition that we'll enjoy using for a little while. OK, so why is this reasonable definition for being reasonable? On your final homework, which is out today and is due in 9 days, and is the last homework, hooray, you're asked to prove 2 things that are consequences of this, which I'll tell you in a second. But first, let's do an example or 2. OK, I'll tell you 2 nice examples about nice properties that random variables have that are consequences of this. But let me step back a second and do some examples. OK, so a favorite random variable in all our life in this class is if x is a uniformly random bit, then expected value of x to the fourth is 1. Expected value of x squared is 1. So it's 1 reasonable. OK, and that's the ultimate reasonability. You can check that actually b cannot be smaller than 1 here. And also, of course, you get more and more reasonable the smaller b is. OK, so 1 is the best. Our second favorite random variable in this life is a standard Gaussian. OK. Well, its expected value of z squared is 1. So this right-hand side is 1. Anybody know the expected value of z to the fourth off the top of their head?
3.
Very good. It's 3. Is 3 reasonable? Yeah. Does anybody know the expected, let's say the 2kth norm of a Gaussian? Or the expected value of Gaussian to the 2k? Ooh. No. It's good. 2k minus 1, you mean? It's 2k minus 1 double factorial. Yeah. Anyway. Great. Yeah, that's a calculation. You can do this. You do like integral by parts, I think. Integration by parts, and there's like a recurrence. Anyway, it's easy. Here's another pleasant random variable, u. Let's say the uniform distribution on the interval, the real interval, -1, 1. You have to do some calculation. Even I don't know what its fourth norm is. I guess you can compute it. Turns out it's 9/5 reasonable. Okay, the exact numbers are not so important, but I wanted to just say that all these dudes are reasonable, okay, because this b is small. Okay, in general, like if b is, this doesn't actually make sense, but like a small constant, we just say that's a nice reasonable random variable. Okay, let's do an example of a non-reasonable, an unreasonable random variable. So let me say y is the random variable defined by y is 0 with probability 1 minus 2 to the minus n. N is just some big number. And let's say it's 1 otherwise. Okay. Sorry. How about minus n? Is that better? Yeah. So expected value of y to the fourth. Well, taking it to the fourth power doesn't matter because it's 0, 1 valued. So in fact, this is also the second moment, which is 2 to the minus n. So on the right-hand side, you have 2 to the minus 2n here, 2 to the minus n. So it's not be reasonable unless b is huge, at least 2 to the n. Okay, you might be like, why did you write as 2 to the n? I mean, it's just some large number, but some large number. Okay, so this kind of random variable is unreasonable, and you know, it's like has this freaky property that it's like mean is practically 0. Well, but with some probability, it actually gets like exponentially larger than its mean, which is kind of annoying. Okay, so those are some examples. Okay, so back to what I was saying before. The mean of, yeah. Okay. Well, another thing is like this random variable is almost always less than its mean. Whereas, you know, a friendly random variable would be like less than its mean with probably like a half or something. You know. Okay. So here are two things that are on your homework, which are consequences of reasonableness. One is kind of simple. It's actually, I put this up here, although we don't really use it much ever. This is like a concentration bound. Basically, it says that if you're looking at the probability that x is sort of noticeably larger than its standard deviation, or let's say its square root of its 2 norm. This is all if x is b reasonable. Now, if you just didn't know anything about x and you were interested in this, then if you use Chebyshev, you would get 1 over t squared. This is like t times the square root of the second moment. And if you use, if you know this reasonable hypothesis, then you can get something like over t to the fourth. Actually, b over t to the fourth. Okay, so that's, if you think of b as like a constant, that's like a bit better than Chebyshev. Okay, I don't use that fact too much because, you know, 1 over t squared is not so much worse than 1 over t to the fourth, but it's an illustration of something that this reasonableness buys you. Okay, here's something that is much more interesting, which you'll also prove, and you can call this anti-concentration. And this says something like the random variable is not too often close to 0. This is for all t bigger than 0. So it's like a lower bound on the exact same quantity. Probability that x is at least t times this 2 norm is at least something, which is a little unusual. I mean, you don't normally see a bound that looks like this, but sometimes you want it. And you can get it if you have this reasonability. It's like this. This is for all, I don't know, 0 less than t less than or equal to 1. Okay, so think of t, for example, in this statement as a half. All right, so then this is like some number, I don't know, 9/16, but it's, you got that probability that x is at least half of its, not standard deviation, but 2 norm is omega of 1 over b. Okay, so if b is, you know, a nice small constant, then this says something nice. It says that actually x is fairly likely to be at least, you know, its standard deviation type quantity. No. So this is only about anti-concentration near 0. So this is also slightly lame. I present it this way because of this issue that this notion is not translation invariant. Okay? So these are all facts, although they're not maybe exactly the facts you'd want in general. So you can get the similar things about anti-concentration away from its mean if you move to the hypercontractivity version of this definition. Oh, I didn't want to erase that. Okay, so all right. So last thing I'll say, imagine that you wanted to, you know, we're always talking about random bits. So all of the random variables we ever encounter are actually like f of x for x bits. So there's some function of random bits. So that's a bit. This is kind of like a bit. I mean, this thing arises for us if f of x is kind of similar to x1 plus dot 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 plus xn over root n. Okay, so you see, this is reasonable. This is also reasonable, 3 reasonable. You might guess that like any linear combination of bits is pretty reasonable. And that's a fact. So that's pleasant. Now what about this? How would you write this guy as a function of bits? Well, you see, to get probabilities like 2 to the minus n arising, you need to combine a lot of bits. Like this guy is actually like 1 plus x1 times 1 plus xn, maybe divided by 2 to the n. That's y. Okay, so you managed to get this probability to be really small, which seems to be something you need to get an unreasonable random variable. But you could say, actually, this guy has a very high degree in the x's. Whereas here, it seemed as if you took like a degree 1 combination of x's, you would probably always get something reasonable, since the 2 boundary cases are both pretty reasonable. Okay, and that turns out to be a fact, and the key fact that one needs for a lot of awesome theorems in analysis of Boolean functions. And one may call this fact Bonami's lemma. This is not a standard name, but it's a lemma in the sense that it often gets used as a lemma. And it was first proved by Bonami, so the name fits. That's what we'll call it. And it just says this. Let f be a Boolean function into the reals of degree at most k. Then f of x is a reasonable random variable. 9 to the k reasonable. Okay, so there's an exponential dependence on the degree, but it basically says low degree combinations of bits are reasonable random variables. Okay, so to state this another way, expected value of f of x to the 4th is at most expected value of f of x, 9 to the k times f of x squared squared. Or, to use this notation, the 4th norm is at most root 3 to the k times the 2nd norm. Okay, so this is the key theorem. We'll prove it next time. And it's also kind of awesome because as soon as you decide to prove this theorem by induction on n, then the proof writes itself. It's very easy. Okay, so you just have to try to prove it by induction on n, and you automatically will.